Hello and a very good evening, everyone. Welcome back to Epsilon 2026. I am Varun Ubale, Media Head of IEEE SIS GST.
And I'm Ishita Punja, the creative head of IEEE SIS GST. We are delighted to welcome you to day 2 of our GRSS webinar series under the umbrella theme From Pixels to Precision Evolution of Sensors in Geoscience and Remote Sensing.
Yesterday, we explored the evolution of remote sensing sensors from multispectral to hyperspectral and SAR and understood how these technologies enable precise Earth observation and smarter decision making. Today, we take the next step, moving from concepts to practical implementation. We now dive into our hand-on workshop titled Hand-on Remote Sensing with Google Earth Engine.
Today's session provides hands-on satellite data analysis with Google Earth Engine using Landsat and Sentinel imagery, bands, resolution, and basic interpretation.
Now let us begin with our much awaited hands-on workshop by welcoming our esteemed speaker for today.
For today's workshop, we have with us Mr. Sujan Parajuli. Sujan Parajuli is an accomplished remote sensing professional with over 8 years of experience analyzing Earth's surface features using advanced technologies such as satellite imagery, LiDAR, and aerial photography. He holds a master's degree in geographic information science from South Dakota State University and is currently working as a consultant in the remote sensing domain.
Over the years, he has successfully managed numerous projects for various organizations specializing in developing intricate remote sensing algorithms to extract meaningful insight from satellite data.
Welcome, sir. We are truly honored to have you here today and excited to learn from your expertise and experience.
We now invite Mr. Sujan to begin today's workshop on hands-on remote sensing with Google Earth Engine.
Should I start?
Yes, sir.
All
You
good?
can start.
Okay. Okay.
Yes, sir.
Okay. Hello, everyone. Welcome to this presentation. So I'm going to present on the evolution of remote sensing sensor from multispectral to hyperspectral and SAR. So I'll be giving first, like the brief introduction about what's the remote sensing is, what are the different sensors from multispectral to hyperspectral to the SAR. Like what are the basic approaches of like doing the process, all those kind of stuff, and then we'll going deep into the like the processing multispectral one. So let me start. So the first one is like what is remote sensing. Remote sensing is just a science of like acquiring information of an object without being in physical contact with it. So it's like taking a photograph from in like the distance place. So taking that information, and while if you see on this, let me my oops, just wait. So if you on this graph, like this, like the remote sensing, like the sensor, and like it's taking the information from that reflected energy and storing that as an information, and then that information is transferred to that ground station, and from that ground station that information is used for application purposes. So like let's say for the Landsat imagery, we have the Landsat satellite or the Landsat sensor that's revolving on the surface, like on the space, and it's taking that like the sensor information from that one, and that information is like the collected information is stored to the like the station, which is Earth observation, like the Eros data center in the US. On that Eros data center, those information like are stored, and then they are further processed. So like when we have this satellite data, we have this level 0 data, level 1, level 2, level 3, like, and so forth. So level 0 data is the like the raw data, so it has a lot of drawbacks and everything. Like when you talk about like the satellites is taking the images from the space. So while it's taking images from the space, it has to go through a lot of like the noises. Like it has to, like we have this cloud, and because of that cloud we are not getting the like the exact or the actual information from the ground. So we have to clean all those kind of information, like cloud or the like atmospheric like the noises, doing some like the radiometric and the geometric correction. All those processes are done on that like the ground station. And then after processing, we call that level 1 data, level 2 data. And those level 1 and level 2 data are used for that application purpose, like for the land cover classification, or doing some mineral explore, like all those kind of agriculture, like the disaster mapping, all those kind of environmental and other application. And while doing that, when we talk about like the sensors from like the multispectral to the SAR one, we have these like how the sources in like the data are collected. One is the passive sensing and another one is the active sensing. So on the passive sensing one, it's it's taking information from that reflected energy from the sun. So on the multispectral and the hyperspectral are the passive sensing, whereas for the SAR synthetic aperture radar, this is the active one. So on that one, the source is the sensor. It emits that energy, and like from emitting that energy, it takes that information from that emitted energy. So the example is the LiDAR or the radar or the synthetic aperture radar one. And another one is like the basic principle that you need to understand is on the spectral signature. So when you talk about the like the remote sensing sensor and one, it has this resolution. So it has this like four different resolution. One is the spatial resolution, temporal resolution, spectral resolution, and radiometric resolution. So this is the information that it acquires, and that's it's needed. So one is like the spectral signature, which is also the spectral resolution. So this is like a digital footprint of that specific feature. So it's like the sensor is taking the information from that transmitted energy. So that transmitted energy are stored into different spectra. So and different spectra means different features. So different feature means different fingerprint. Let's say for this on this graph on this like the vegetation. So like for let's say for the vegetation one, like the our eye sees it as a green base because this green light is reflected. So that's why we are able to see that one. And but like our eyes, like our human eyes sees only the visible range of rays or the wavelength. So but beyond that we have this ultraviolet, like the near infrared, x-rays, all those kind of like the wavelength that we cannot see, but the sensor it acquires that information. So like with like the like the advantage of remote sensing as it acquires a lot of information besides that, like what we can see. Like we can see only the visual range, red, green, and blue. Like we call that true imagery. But beyond that, that sensor collects other information also, and that other information are useful to to classify different features. And in order to classify different features, let's say for the healthy vegetation, it absorbs the red light and then it reflects that near infrared light. Like we cannot see that near infrared light, but like the science is that it reflects that near infrared light. And using these like the features or the like the advantage, we can able to detect whether that vegetation is healthy or not. So like the idea or the basic premise or the basic like the principle is that this healthy vegetation, they absorb the red light and reflect this near infrared light. And based on that we create like the vegetation index, call as like a normalized difference vegetation index, which is used to detect that like the vegetation healthness. So like the application of this is, like let's say you want to classify a forest area, or if you want to like calculate the carbon, carbon density, those kind of stuff, you are using this NDVI as an index. And in order to calculate that index, you are using these two bands. One is the red band and the near infrared band. And those red band and near infrared bands are the information that is stored on the sensor. Okay. For example, the water one also, it looks like a dark one because it absorbs all those ones. So it's like it appears all dark. And in like there are other different features. Like so, this is for like a land cover classification. So if you see on the graph on this one, you see this the green one represents the like the green or healthy vegetation. So if you see on like from 0 to 0.4, after 0 point like 0.6, it's going upwards, so that represents it's a healthy vegetation. And if you see on the on the blue one, which represents the water, it doesn't reflect much, so that's why we have this reflectance, or the wavelength is very, like the reflectance is very low, like it's below that 10%, like if you see on the y-axis is the reflectance, it's very low on that one. For the soil properties also, that one, like like this is the fundamentals for extracting information or extracting features from the sensors. The other one is, like I already said, like it has this a lot of this electromagnetic spectrum. Our own eyes only able to see this visible light, but there are others as well, and that sensor, it collects all those kind of information, and those kind of information are the the advantage of that, like the remote sensing, which we use for a lot of application. Okay. So let's say, like a Landsat and the Sentinel, we call that multispectral one. So it has this, like the band from 3 to 10, 10 bands. And, like on that one, it has this red band, blue band, green band, near infrared band, short wave infrared band, and so forth. And those bands are used to classify into different features. And also the, like another concept that you need to understand in remote sensing is this resolution. Like I said, like the spectral resolution, I said like different band information. Beside that one, we have this spatial resolution, which is the pixel, like the pixel length or the pixel size. So the idea is, like let's say on the Landsat one, the pixel size is 30 meter. What does that mean? Like the 30-meter pixel size, it means, like the one, like the 30-meter means the square, the pixel is like the, if you see on this one, it's zoomed in, and it says like you see the square, like square dot, like the square one. So this one, it represents one pixel. So one pixel means one information. So how the info, like the how the information are stored on the sensor is like on one pixel, like it's acquiring that information as a one, like let's say like one number, this represents like a value of 1 2 or something, like that represents one feature on the ground. So one pixel represents one feature on the ground. So let's say if a pixel is resolution is 30 meter, then one pixel represents what is like 30 by 30 is like a 900 meter square. So whatever is within that 900 meter square area, that is stored as an one feature or the one information on the sensor. So that's why, like higher the spatial resolution, higher granular, less granular or the less coarse. So lower the spatial resolution. So if you have the spatial resolution of 1 meter, then we have much detail on the ground. When we have this 100-meter spatial resolution, then we have less detail on the ground. So higher the spatial resolution, less the detail. Lower the spatial resolution, higher the detail. So that is one concept. And based on that one, like one advantage is like we'll have more, like the spatial, like granularity on the ground. But the disadvantage is like it depends on your in your project. If you want to cover a large area, then or if let's say for the land cover classification, you don't need that much of detail, then 30-meter resolution might be fine, because your your project or your objective is to cover the large swath of area. Then on that sense, like 30-meter, even like the 100-meter one is fine. But if you want to extract a lot of detail on the feature side, then high resolution is fine. High spatial resolution is fine. In like the spectral resolution I talked about, in like it's the number of wavelength, or in like the band information. The other one is the radiometric, is like it's the bit depth. So in like the with the 8 bit, you will be storing like 2 to the power is like 256 or 255 information on that one, whereas 2 bit is like 0 and 1. And we have like a 8 bit, a 16 bit. It's like how much detail you want to store on that sensor. And the other one is the temporal resolution. So temporal resolution is like, let's say for the Landsat one, let's say it's starting from one point, and the number of time, or the amount of time it takes to return to that initial point of acquiring that information, we call that temporal resolution. Let's say for the Landsat one, it takes 16 days. So like the temporal resolution for the Landsat is 16 days. So what does that mean is, like if you want to understand the change detection, let's say a fire occurred on certain place, so we want to know what happened pre-fire and to post-fire. On that sense, in order to get that information on that specific area, then we have to wait like 16 days. So in like Landsat may not be a good idea, like the good sensor for detecting the fire. So on that purpose, we use the MODIS one, which has the temporal resolution on a daily basis. So it's like, because it has the spatial resolution of like 100 to 300-meter, but the temporal resolution is very high, which means like it's orbiting that place on a daily basis. So if you want to see like whether the fire occurred on that place and everything, then MODIS is good for detecting that fire. So that's why, like on the fire detection and everything, like the wheels or the MODIS, we use that MODIS sensor. So we have these different sensors, and then they have their different like the applications and everything, and all those applications depends on this, like what kind of spatial resolution is it has, what, like how many spectral resolution or the spectral information does it contain, what's the radio, like what kind of information does it contain, and also the revisit time or the temporal resolution. So all these factors like determine what kind of sensors you want to use for your project, or for the specific like the application. So first, like we will go with like this multispectral remote sensing. So what is multispectral remote sensing, what are the different approaches and everything. And multispectral remote sensing, we also call that a gateway to the earth observation. Okay. So what is multispectral remote sensing? It's acquiring, or like the collecting the information in a handful of in like the spectral information, like generally 3 to 15 bands, and that 3 to 15 bands usually within that wavelength of like the visible band up to that the near infrared band, SWIR band, thermal infrared band, like those kind of band. And this one focuses like the multispectral imaging, or the multispectral remote sensing. It focuses on the broader region of this electromagnetic spectrum. That's why it's covering the large area. That's why it's good for like the efficient and large scale data collection. And like the common example of the multi like the spectral remote sensing represents Landsat data, Sentinel data, and the MODIS data. Okay. So how this multispectral imaging are used in our day-to-day life? Like what are the different field or area where those are used? So it is used in agriculture and vegetation monitoring. Let's say for this forest and wildfire, like the management. So let's say a fire occurred. So MODIS is used to detect where the fire occurred. But after the fire occur, you want to estimate how much forest has been destroyed, like how much carbon has been like they're destroyed on that area. So on that purpose, like Moody's, it has, because it has this high spatial resolution, means it has lower detail. So on that purpose, it's better to use the Landsat imagery or the Sentinel imagery for that particular time frame. Okay. Also, like the pest and disease detection, so it's all based on that vegetation indices, like because of the pest and disease, like the infection or the like the infestation, the forest area, it colors changes, like one of the examples is in South Dakota, like the blackish, because of that mountain pine beetle, like all those pine trees, they turn, into red and everything. And how to detect whether those areas have been, like infested by that, like the insect or the beetle. It's like it's taking the information, like they taking the imagery, and like the healthy vegetation, it the color is green, whereas for the, like the infested one, it's red, or the, like the brown, or like those kind of color. And based on that difference in color information, we are able to detect, okay, there is this pest infestation, or there is like insect infestation on that area. It is also used for, like soil and mineral mapping, like mining and exploration one. And also, like the water quality analysis. Let's say we have a lake one, and you want to like calculate the algal bloom, or like the harmful algal bloom on that area. So on that one, from the remote sensing sense, it collects that in like the near infrared band, red band, all those kind of band. And then we have these different vegetation indices. So on that one, this one we use like the NDCI, like normalized difference chlorophyll index. So we have these different indexes for these different purposes. Let's say for the vegetation one, we use NDVI, like vegetation index, whereas for this, like the water one, like whether that's water is polluted or not, we use ND, like the chlorophyll index. Okay. Same thing for the, like the mineral mapping, fire detection in like NBR, normalized bond ratio, and so forth. So one thing is like the MSI, it has this like 3 to 15 bands, but it's in use. In like the first, in like the Landsat satellite imagery that went to the space and start collecting is like, it has been like more than 40 years. So it has been more than 50 years, but still we have been using that one. So, like the more is better, but still it has this in like the limited number of spectral information, but still we are using. Why we are using? What's the power, like the superpower for that one? One is like it has this in like it collects that on the visible band, which is like you can just looking at the images, you can detect, okay, this is water body, this is buildings, this is forest, like this is agriculture. Beyond that one, then you have to use other in like the spectral information. So like it acquires that information on the visible band rate. Another one is it has on the near infrared band, which is used for in like detecting the healthy vegetation, calculating that NDVI, and so forth. And another one is like short wave infrared band. So this band is used for soil and mineral composition, like the water content detection. Let's see, for the NDCI we use the SWIR band. Okay. And also for the wildfire monitoring, because for the drought and like the water, because it depends on that water presence. So, and also on the soil analysis. Okay. So this one is like the spectral band, like it. I have already covered this one. Let's go beyond that. So how do we process, like the typical multispectral imagery? The one is like the first step is like the data acquisition. How those data are acquired. So like the multispectral data is collected from satellite platforms such as Landsat, Sentinel, Modis. Like they may have like higher spatial resolution or like higher temporal resolution, and those data We can directly acquire from the USGS Auth Explorer one, or the Google Auth engine. So those are the sources where we acquire those data. Okay. Then after you get the data, you need to do some pre-processing. So like you have to do some correction on the side of like the atmospheric correction, radiometric correction, and like the geometric correction, and so forth. Like one thing is like like when this sensor, they extract the information, they extract that information as a digital like DN numbers, and on that DN numbers you have to convert that into reflectance, surface reflectance, or the top of atmosphere reflectance. So in order to convert that one, let's say for the Landsat one, you divide that number by 10,000, because those DN values, those are stored from 0 to 10,000, because it's on the it's stored on the integer in like the 16, on the integer 6 8 1. So in order to calculate like different vegetation indices, first we have to convert that dn values into the in like the reflectance one, and after that the reflectance one, you calculate a different vegetation indices. So all those stuff we do on the pre-processing side. Okay. And then comes this data transformation and like the enhancement. So after you do the pre-processing, you calculate the different vegetation indices. Let's say what's your purpose is, what's your objective is. Let's say you want to classify land cover types, then on that purpose, you might be needing that ndvi one. Let's say you want to classify different water features, then on that one ndwi, like wetness index, might be a good in like the vegetation indices for that one. So based on that, like you have different indices like ndvi, like I'll be covering that as well, like ndvi, sabi, which is like soil adjusted vegetation index. ndwi is for the water bodies. So you are using, it's all like the indices, like it's like the formula for calculating different like the features. So after you calculate this, like different vegetation indices, then you do this classification and analysis. Let's say we want to do the land cover classification. So on that first process, we acquire the data, we do some pre-processing, and then we calculate the NDVI. So NDVI, we call that normalized one. So when we say normalized, it means the value is in the range of 0 and 1. So so the values are in those range. So now you want to classify into like 5 different classes, like vegetation, like forest, agriculture, built up area, water bodies, like the barren land, and so forth. So on that one, you are classifying, let's say like the vegetation one, because the reflectance is high. So you will be assigning, let's say 0. 0.4 to 0.8 is for the vegetation. For the water bodies, because the reflectance is very low, in like the value from 0 or negative is assigned for the water. And similar things for the in like the agriculture, all those kind of uh, like the features. Okay. So that's why you do the classification. So on the classification, you can do with the like the one I said is like unsupervised one. You can do with the supervised one also. Like you go to the field, collect the data on that field, and based on that, you have this label data. You can do classification. That is like the machine learning part. Okay. But this is the basic idea. And once you have this classification, let's say land cover classification, then you visualize that as like through the map, and you interpret that one. Let's say you are doing land cover classification on your area of interest, then you want to classify like they get the information, like how much area is land, like the forest, how much area has been covered by agriculture, and so forth. So this is all for the interpretation and visualization. So what are the different tools we use for that processing? So on the GIS side, like the QGIS and the ArcGIS. So QGIS is the open source GIS software you can download on your system. It's all free and everything, whereas on the enterprise level, or the like the paid version one, is the ArcGIS one. So this is the popular, like the two popular software which is used for data visualization, processing, analysis. Whereas on the open source one, also you can use like the Python libraries like the Rasterio, GDAL, and those kind of stuff. And also you can do that processing on the cloud computing, such as in Google Earth Engine on the AWS. We have this other like the from the ESC or the Copernicus one. We have this Snap tool as well. We have this Equalite tool. So these are like the common tools. Okay. And what are the like the challenges or the limitation of the like the multispectral one? So one is like the weather dependency. So the cloud cover is one of the like the topmost like the limitation of the multispectral one, because like it can be affected by cloud, like making it difficult to obtain the clear data for that field. Also we have the sun angle also in like the how the sensor is collecting the data. That sun angle, you have to adjust that sun angle as well. And also in like it has this limited spectral information, the pure band, so higher the better. So that's why like it has this pure band means we are not able to collect a lot of information for the ground. And also the data processing requirements. So like if you are working for a limit like the limited area, the small area, it works fine. But if the like the analysis or the processing is for the regional scale or the like the country scale or like the global scale, then the data is a lot. You have to process a lot of data. Like normally for the Landsat one Landsat imagery is around like 100 of megabyte. So like when it's collecting the data, it's collecting as an tile. Like it's it's taking that information as an tile. So if you want to cover a lot, like a lot of area which requires a lot of tiles on that one, then a lot of processing power, processing time, those are also one of the like the limitation. And one thing, like we have some myths about like the MSI. It's like it's able to identify all the features. It's not true. Like it provides both spectral data, but unlike in like hyperspectral imagery, it's not able to extract a lot of information. And one thing is like it can see through cloud and smoke. That's not true. Like cloud, smoke, or the atmospheric, like the noises are the biggest drawback for that one. And all sensors have the same quality is also not true. And processing is simple. That's not true. And how to make these like MSI most accessible, then we have to like one thing is we have to work on this standardized data formats. So like we used to store the like the imagery for before like T format, but now before like T format, then we have to do this geometry correction like a geo reference one. So geotiff is the geo reference in like the raster file, and also the GeoJSON one. So those are like easier to like load the data, extract the information from that one. And also on the cloud and everything, we are going to use Stack as well. And also like for making that processing like accessible and everything, instead of doing that on your local system or a local computer, now it's switching to that cloud computing one. And one of the advantage of cloud computing is that you don't have to download the data. Let's say I want to use the Google Earth Engine, so I'm using the like the data that is stored on their system. I'm not downloading that, storing on my folder and doing processing. So like downloading the data, storing on your system and everything, like those has been cut out uh, if you do that on the cloud computing. So that's what we are going to do on the Google Earth Engine in like coming to play in like Google Earth Engine application. And also like the simplified analysis and user friendly tools also, like QGIS, and also making process much easier for everyone to understand as well. The other one is like the hyperspectral remote sensing. And in like multispectral remote sensing, it collects the band from 3 to 15 but when you have a lot of like the spectral information in number in terms of like hundreds, like 200, 300, in like the spectral information, then we call that hyperspectral one. And the sensor example includes that emit, sensor, prisma, nmap, and so forth. And the same thing, like how it, like the difference from the multispectral and hyperspectral is like hyperspectral has a lot of band information, like it has a lot of spectral information on that one. So it has like it's able to extract, like let's say MSI spectral is like the digital fingerprint, so it has a lot of detail on in that sense. Like hyperspectral imaging has a lot of like the information in terms of spectra. So like they are same in like on in terms of like application. It's used in agriculture, sewage, in like the water quality, human application, disaster management, and so forth. And same thing, like how do we process like data acquisition, then you do some pre-processing, and then you should, because on the hyperspectral one it has a lot of band information, so it's like same like the, because the like the narrow band, because of that the narrow like the difference, both like two or three bands are maybe collecting the same kind of information. So on that, it's like like when we are doing on a like the machine learning one. So you, when we have a lot of variable, it's good for the model, but it's not always the case. When we have a lot of variables or the parameters for developing that model, then we have to do some cleaning, like the variable importance or like the principal component analysis to uh, identify which variable is good enough to explain that output. So like, because like we start with the simplest one, like if one variable is good enough to explain your model, then you start with the simplest one. If it is not, then you keep on adding different variables. Same is with this one. Like if you have like a limited number of spectral like the information that's enough to like extract the features, then you don't need a lot of spectral information. So on that one, you have to do like the data cleaning or the noise reduction, which is just in like the segmenting out, like segregating that in like the spectra, like a lot. Because when we are talking, it's not in the tens. Like on the multispectral one, it's up to maximum like the 15 spectral bands. Whereas on that one, it's on the 100, like 200, 301. So we are just reducing that spectral to like 200, 300 to let's see on the like tens or 20s. And similar like the feature, like after this you do the feature like the feature extraction, classification, same stuff. And on that one, like most of the time we use like the QGIS, Python libraries, the cloud platform also. NB is another like the remote sensing software, which is mostly used for the remote sensing, like the raster data in like the analysis and everything. Like the ArcGIS one, which is good for the GIS one, but it's not that good for the like the raster processing and everything. But the NB one, it's very good mostly for the raster processing. And in like the geotiff and geojson, it is for in like storing that information. It's easier to in like the extract or the read the information from that file format. And also like the limitation, it has the same limitation because it's the multispectral in like it's in like the passive sensor. It has the passive sensor, that's why cloud and smoke, low light condition, in like that data complexity, because it has this massive data volumes. And also data cleaning and stitching, because if it is stitching means we have collected that information on a tile basis, and then we have to in like a mosaic or the merge that tiles into one, like the one, like if you are covering the large area, then on that part, like stitching is also one of the like the bottlenecks. Also we have a lack of standardization so far, like market is fragmented, and lots of terminologies and everything that's still very hard to understand. And what's the key myth is just like multispectral images, it cannot detect through like soft surface one. It cannot go like in it, it cannot penetrate through that surface. So it just collecting the information that's on the surface. That it cannot work in like any environment, like weather. It's dependent on the weather, cloud, those kind of stuff. And one more thing, like that's the biggest one is like more band means better results. That's not the case. So even the multi, like sometimes multispectral imagery might be good than the hyperspectral spectral one, although hyperspectral has a lot of band information. And hyperspectral is like not like a one size fit all, like it's not going to solve every problem. Like we have to integrate like other like synthetic aperture, which is the active sensor, lidar. And for like making that accessible, one is like we have to we have to come up with this standardized protocol or the standard of practice. Also we have a lot of jargon and like the fancy word, we have to eliminate that, make it understandable, reducing the in like the intermediary data, and also using in like the user friendly platform in like in like open source, mostly the open source and freely available one, so that all people have access to it. The other one is the synthetic aperture radar, which is like the active one. So it's like like I have a camera, so like on a broad daylight, it just takes an information. But like on the like the where the light condition is not that good, then it flashes the object, and which is like it's providing its light to extract that information. So synthetic aperture is like that one, like the lidar one, SAR one. It's the basic idea is like that one. Like for the passive one, sunlight is illuminating that surface, like that features. Whereas on this one, the sensor itself does that one. So it is an active remote sensing, like technology that sends out pulses of energy and records the reflected signals after they interact with the Earth surface. And based on that, like it captures detailed images on like how radar waves interact on with the physical features and surface condition. Like the examples include like Sentinel-1 data, LOS-2, TerraSAR X data. Okay. And this one is used for like land and surface monitoring, land use and urban planning, agriculture one, forestry and deforestation. So where like multispectral imagery, it, like for the detail one, in like the SAR is used. Disaster and risk management, like this has been used recently, like a lot of time, like flood monitoring, like oil spill detection, those kind of stuff. Because where like it can work during other like other like weather condition as well. Okay. And also mostly on the military and intelligence. So on the sad one is a little bit complex in processing and everything, and still like we have been focusing most of the time on multispectral, hyperspectral one. So it's still the in terms of processing, it's one of the difficult one. So like the but the like the process is similar. Like you collect the data, then you have to do some calibration and correction, and then you have to do some filtering. That's the hardest part on this one. And then you do the data analysis and in the visualization, like all those stuff are like similar to the like the previous one, but this one is more complex than the multispectrally processing. And this has been like used in a recent time, so it has a lot of spoke on that one. And what are the different tools? So we have this QGIS, like the open source one, Python and MATLAB libraries, this NV, like the cloud platform, and like all those kind of tools. I'm just listing out some of the like the commonly used one. there might be more than that. Okay. And what are the like the data complexity, like the limitation or the challenges? One is this, like it requires filtering, because this is the, like it has a lot of noise. One is the speckle noise. Another one is the complex data interpretation. So like with the Landsat one or the multispectral one, you load into the, like the software, and you can see the information, or you can visually see that one. But on the SAT case, it's not like that. So it has this, like the VB, has like those kind of information you need to take into consideration. And also one is like it's had this high data volume, geometric like calibration and correction, and other like the environmental like physical like limitation. Although it can go through that atmospheric like the cloud and everything, but like the shadowing or the foreshortening might be an issue for this one. And also it cannot undergo that like the penetration. Like it's not like, although it's used for the like the mineral exploration and everything, but it's not that it's extracting information underneath the surface. Okay. And another one is like the spectral indices, like I said, like the NDVI, like NDWI, those kind of stop. Why is it important? So like when we are talking about this satellite remote sensing, it has you will revolutionize this environmental monitoring, because it has this a lot of information for this analyzing different land cover types and other use cases as well. you know and for that purpose, you use this spectral indices. So it's used for assessing the healthy vegetation, soil condition, water quality, and so forth. And it's used by like resource managers, scientists, like other people as well. So how what can satellite sensor detect? So like on the visible light, like just looking at the like the photo or the imagery, you are able to classify into different land cover types. But like when we want a much more detail, then comes that other information, like near infrared one, swear, like all those kind of band. So like the near infrared band is one of those band. It is used for like healthy vegetation detection and biomass estimation. Shortwave infrared band is used for soil moisture, bond stability, mineral composition. And then we have this thermal infrared band, which is used to like measure the surface temperature, or the temperature one, or the thermal properties of materials. And microwave and radar one, which is used for like the cloud penetration, and like it's like all weather dependent one. Like we can collect information at all weather. So what is spectral indices or the vegetation indices? Then it is just a mathematical, the formula, the combination of different reflectance values or the reflectance bands. And for that one, you can use either like two or more bands, not three, like the more bands. Let's say for the NDVI one, we use like two bands, whereas for the EBI one, we use three bands. And there are lots of like thousands of the spectral indices. And they are used for like the land and aquatic monitoring, either for vegetation health, ecosystem changes, and so forth. So you see, like this is some of the widely used in the environmental application one. Let's say for the NDVI one, the band that we use is like near infrared band and the red band. And this one is used for vegetation health, like a land cover classification. Another one is like the enhanced vegetation index, or the EBI one. We are using like three bands on this one, like near infrared band, red band, and blue band. Similarly, for the NDWI one, we are using two bands. So like these are the different, like the common, like it has a lot of, like you can create your own as well, but it's it has a lot of applications on that one. But these are the commonly used one. Okay. And another one is where we do that, like the processing, like Google Earth Engine. It's not a traditional GIS software. It's a cloud-based platform for doing a large scale computation, or the processing. It's not for doing that megabyte gigabyte scale in like the process. It's for the petabyte scale, which is bigger than terabyte as well. Okay, and this one is for like the server side processing, and also it had this advantage of parallel computing, which means like you can do that multi processing, like you can do processing all at the same time. So on that one, like the on the API side, we have this Python API and the JavaScript API. Like we have this JavaScript is like web based in like the IDI, which is used for in like the rapid prototyping, algorithm development, and quick visualization. So if you go on the code dot go like on this link, then it goes on this link. It opens that in like the IDE. On that IDA, all you do is on the JavaScript. Like you need to understand the JavaScript, but also you can do that using the Python API, also using the Google Colab, like the Gmap and everything. You can use that one. And on our like demo one, since I'm comfortable with the like the Python API, and Python is mostly like the handy for the like the data analysis, data interpretation, and everything. We'll be switching to the Python one, and we are using Python because of that. Okay, so we have this like the Google Colab. You can use Google Colab like the cloud platform one, or you can use on your local setup as well. Like on the Google Colab one, you need to have one thing. You need to have is just a Google account. So on that Google account, you can log into the Google Colab, and then it's like you are not setting up any environment on that one. The advantage is one, but here you can like you can install the spider or the like the VS code, all those kind of software, and then start processing from that as well. But on this one we'll be using mostly the Google Colab. So what's the the basic like the process for doing that? One is like the Google Auth Engine authentication. So it's like the process of linking like this your environment. Let's say either you are using Python environment or the JavaScript environment to this Google Auth Engine account. So you have to do once per process. Okay, so what are the first step is like first you have to import that library, which is the Auth Engine, or if you are using for the Google in like the Pythonic version one, the Gmap is like widely used nowadays. So first you have to import that library, then you have to do the authentication, and then after that authentication, like it asks to access your folders like Google Drive. After you provide that one, and also you on the Google Cloud platform, you have to create in like the cloud project where you will be storing all those information and everything. So you have to provide that authentication information. So it is all under that like the setup one. So once you have the setup, then you can go through that in like the data acquisition and everything. So once you so this is the initialization. Now on the like the data structure is like we like I said, it's on the cloud computing. We are not downloading anything like any data. We are just like it's stored on the Google Earth Engine, and you are just whatever the data you want to use for your specific purpose, you are acquiring that information from that server. Okay, so you can either access like the single imagery or the image collection or even like the vector data. So let's say if you go on the image one, you see like the objects how they are collected is, you see, oops, it's taking some like image, like here image is collect like this is the like this is the folder within that Google Earth Engine where those like sentinel imagery is stored. So you are just like giving some like the filtering, like okay, I want the this is the like the location of your area of interest. So I want the imagery for this area of interest, then I want the images ranging from this date and also you can specify, okay, I want the images with only this cloud percentage. So based on that, this one helps to acquire that image from that one. So once you get that one, like, okay, you want only this like three bands or the like the four bands, and based on that band you can do like the further processing, like vegetation indices, calculation, classification, and so forth. And same thing with the image, like the like image is for the single image, collection is for like the group of, like the collection of the images, and also like the feature collection is for the vector data or the polygon or the like the all those vector data, like maybe the road data, like the polygon one, like the administrative boundaries, like all those kind of stuff, or the, like even the point location. And what is the like a data filtering workflow? Like how do you do that on a Google Earth Engine? So first is you load the collection. So like you can load using the entire collection. Let's say on the image collection one, you see this is the Earth Engine catalog. So it has a lot of, let's say I want to go to the Landsat one. You see on that one a Landsat. And then these are the different Landsat information, like on the Landsat one, they have the data from 2021 to 2000, like the present one. If you want to go with the oldest one, then we have this Landsat 1 to 5, which is starting from 1972 to 1999. The Landsat, let's say I want to acquire the data for 2015, then maybe Landsat 8 is one. So if I open this one, so you see on that Landsat 8, it has this surface reflectance one, top of atmosphere and raw images. Like I said in the like the starting one, when the satellite this acquired information, they have this level 0 data, level 1 data, level 2 data. So this raw images maybe level 0 data, but top of atmosphere surface reflectance is level 1 data, which is the processed data. Okay, so instead of using the raw images, you want this in like the surface reflectance one. Let's say for the vegetation classification and everything, we want to use the surface reflectance one. So with this one, you don't have to do that. Like that pre-processing is skipped because you are using level 1 data, and they have this level 2 data, which is like they already have the data for the NDVI, like different vegetation calculation. Okay, so let's say I want to acquire this information like surface reflectance one. So if you see on this Landsat, in like Landsat, so this one is level 2 data. Okay, so USGS Landsat 8, this is the sensor level 2 data, and this is collection 2. So on that one, if you like on the Google Earth Engine, how to like the acquired this data is using this is under this Landsat 8, CO2, T1, like top T1 L2. So this is the folder where this data are stored within that Google Earth Engine. So this is the like the location information you need to provide. Okay, and here it provides a lot of information. Like it provides you the description one and also the band. Because this is a multi-spectral, like the band one is like the surface reflectance, which is like the blue band. Band one is blue band. Band two is red like this blue, sorry, band two is blue band. Band one is like coastal aerosol. I think band one is a noise. Band two is blue band. Band three is a red band. Sorry, band three is a green band. Band four is a red band. Five, you see it has all those band information. So you can either like load all those band, or let's say you want to just calculate the NDVI one. So on that one, what you need is only the near infrared band and the red band. So you can only use in like near infrared band is band 5 and band 4. So you just filter that to get just only these two bands, and then do that further processing. Okay, so it has a lot of information, and also it provides like the code, like on the collab one, how to do that one, like for the data set one, this is the collection where you are acquiring the data, and then you are filtering that by date. So like I want to date, like the data from 2021 to 2000, like the May to like from start of May to the end of May. So, and also it has that, the scaling one is because for that scaling it's multiplying that by 0.00, like for each of those band. And after that one, it's visualizing. This is on the normal visualization one, and then like this is like on their like the documentation, they have even provided like how to acquire the data, how to visualize the data, like that one. And if you are comfortable with the JavaScript, they have provided this one as well. So this is like the basic one, like how where to acquire the data, how to acquire the data, how to do the filter. Like here they have the just filter by date, but you can filter by the like the metadata, such as like the cloud percentage, even by the location and so forth. Okay. So if you see on this one, like we can filter by the area of interest. So like you either you have your like the area of interest in Polygon, or like the location information, you can do that one. And for that one, the function that we have to use is like the filter bounds and the AOI. And you can also filter by date. Let's say like on the example that I showed, like from 2021 May 1st to the June 1st, which is for that 1 month time period. So you can filter that date. And also you can filter by metadata also, like because like when we are doing like the processing analysis and everything, uh, less cloud cover is good. But when we don't, like 0% cloud cover is best, but for your specific area of interest, you may not find that much of detail, like the data. So you can specify like this one is like cloud cover 20, means like 20% cloud cover is fine, like 30% cloud cover is fine. Okay. And that's all for this one. Do you have some time for the demo? I can show you one demo. Okay. So one I can. Okay. Um, Let me share. So on the on the demo slide, I was just giving a brief, like the demo of how to acquire the data, how to like the do the visualization on the like the Google Earth engine. So the Google Earth engine and Gmap basics, like I'm doing all this on the Google Colab. So if you go on the like collab.google.research.com, so one thing you need to do, you need to have is, so once you go to this collab.google.research.com, then either you have this like the Jupyter notebook file that already like you have done, or you can create a new notebook, and then like you can now start like the coding, do they start the processing. So you are not using your resources, you are everything is done on the Google Earth Engine app, in like the Google platform. So Google Colab is one of those. So on this one, we don't have that hassle of like the creating an environment, setting up the environment, like installing all those packages, like all those kind of things have will be skipped when we use this one. So once you do one, like you can do like start like import OS or print. Then you are good over there. Okay, so that's what we are doing. So here first thing is, like here it has its own folder also. You can, although this is temporary, if you want for the, like the longer term, then you can mount your local drive or the Google Drive, like for all those output data and everything, you can store on that folder. Because if you use on this default one, once you close this one, it's all gone. Okay. So 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 the first one is like, you set up the Google Earth engine. On that one, you can either use like the Earth engine, like the Earth engine libraries, or the Gmap libraries. Like if you don't have that installed, then you can install that one. So using that pip install, which is normal for like the setting of the environment. Like if you have some ideas like how the Python works and everything. So once you have that one, first thing is like, you are importing the libraries. So I'm importing the libraries, and then first thing is like, if you don't have the Google Auth Engine account, then you have to go here, create your account, Google Auth Engine account. So like once you have this account and everything, you can set up over here like remote sensing class. Like I'm creating a project called remote sensing class one, and then I'm using that one. So you have to create this one. So I've already created like RS class one. So I'm like I'm importing that one. And second thing, like I said before, like you have to authenticate and initialize that project. You created a project on the Google Cloud Platform, and then you have to authenticate on that one. So if I authenticate this one, yeah, and then you have to initialize. So now we can go with this interactive mappings. Let's say I started with Google Map, and then if you want to display, you see it's displayed over there. So let's say if you want to go like somewhere over here, like Mumbai, like Navi, Mumbai. That's I think where this university is. So you can zoom in, zoom out, like it's like more interactive one. It's like loading on a GIS software. And then if you want to filter, like let's say if you want to center on your point of interest. So this one is, I just Google it, the location of that Navi, Mumbai, like your area of interest. And then I set up the zoom level to that, like the 14. So you can play around with that. And like if I play this one, it you see it's pointing me to that one. Like if I zoom that to 5, then it's zooming out. You see, it's zooming out. But if I go to 14, that is zooming to that location. So you can play around with that one, or even you can like select your area of interest, or like if you select your point of interest. Like it has a lot of functionalities on that one. So those are the same thing. Yeah, and you see, like you can also like load the different base map. So one thing is like, like we can add a lot of base map. Like I can add base map as in like the old imagery. Like this one is like the normal one. This one is with the imagery one. You see the on the imagery side. So with the imagery side, let's see if you go. Where is India? Yeah. On the India one, you see on the satellite imagery way how it looks. And like it's able to, you see this is like on the satellite imagery. This is the like the true imagery. With this true imagery, you can identify. Okay, this is the water bodies. This green seems like to me, like the vegetation of the forest one. In like this brown one, if you zoom in, you see on the feature one, this is like the agriculture part. So for the land cover classification, you can either use this in like the true imagery, just using that red, green, and blue band. But if you are not able to distinguish between whether this is barren land or like the agricultural land, sometimes it's very hard to like detect that feature. So in that sense, when our eyes is not able to classify that feature, then we use other band information like near infrared band, uh, and so forth. Okay. And also, like another one is like the world topo map. You see, like the land cover one. If I do land cover, like the topo map one, you see over here. Like if I see on the topo map, is it like a topographic map? And also it has a lot of, like if I want to list out what are the different, like the base imagery available within the Google Earth engine, like the Google map, then we have like 1531. And if you want to list out only like 10 of those, and based on that you can use any of those. And also you can, let's say, just for this visualization one, you can add the text at the bottom, like you can, for the visualization purpose, you can, it has like a lot of different those, like the functionalities. So, and it also has this layer manager, like you can, like you can use either that. You see, I'm selecting one single imagery, and then also I'm using you to like the select the vector data, which is like the state data for this state of like it's for the United States. So if I run this one, this one is for let's see. So this is the single imagery, which is the digital elevation data or the elevation data that it's for the whole world. Okay. So I'm loading this data. So if you want, okay, see, if you want the elevation, what the elevation feature for your area of interest, then you can do so. Like you can select area of interest, and then okay, on this area we have like, like it has this, like the green represents the lower elevation, this light color represents the higher elevation. Like you can have a lot of information on this one. So on this one, what does this represent? Like this color represents, you can go with this metadata of that single, like the image. Like I said, on the Landsat one, it has a lot of information on the bands, like the description one. So if you want to get a lot of information on this one, like you can go directly on that one. And you also can specify how to visualize one. Here I have specified like the minimum value, like the minimum elevation is 0, whereas maximum is 4,000 meter. And then I am, like representing that into like the five different color. Okay, so you can specify that one. And also I'm specifying, like the layer name. I'm specifying the layer name, and also like I don't have that US states over here. So this is one. And also you have this inspector tool, like another one is like I want to just acquire, like the get the information for this SRTM, which is another elevation one. Okay, but here I also want this Landsat data as well. You see I have this Landsat image, Landsat 7 top of atmosphere, which is the 5-year average. And we have this data from 1999 to 2003. So if I want to load this one, you see for that area of interest, I am visualizing Landsat with this band 4, band 3, and band 2. Okay, and then I'm specifying minimum value is 20 and maximum value is 200. So if you see, like I don't see Landsat. If you see with this, what is Navi Mumbai? Okay, this is Navi Mumbai. Let's see. So if I want to see on the Landsat one, you see, I think this is the one. You see, this dark represents the water bodies, whereas this like red light represents the vegetation. You see, these are like I see. I think it's a park or something. Yeah. So this is the Landsat. Like you see on the land, like Landsat is like 30-meter one. You see, when I try to zoom in, it just pixelate out. I don't see much detail on that one. But if we have this higher spatial resolution, let's see, this is for the Landsat one. If I use the Sentinel one, then if I zoom into this one looks like to me like the airport, like the runway for the airport. I'm not sure what it should be like that. Yeah, this is the Chhatrapati Shivaji Airport. So on the Landsat imagery, I'm not able to zoom in and get that detail. Okay, and then we have this all a lot like this is like the simple visualization. And now let's do some uh, like the vegetation indices are like the calculation. So let's say like this is for the filtering image collection, filtering image one. Let's see, what is that one? Feature collection. So you see on the NDVI one, like using this Landsat data, I'm calculating this NDVI. Like I said, like the basic understanding. Like you have the data, you acquire the data. This is the process. I acquire the data, and this since this is already like one to level two data already pre-processed. You are not going to do all those kind of pre-processing stuff. And then another one is calculating the different vegetation indices. So on that one, I'm calculating the NDVI for 1999. So NDVI is the vegetation indices which uses that near infrared band and the red band. So here I'm using, like the formula. The formula is a near infrared band minus red band divided by near infrared band plus red band. So that's what I'm doing. Like, I'm selecting the near infrared band and I'm selecting the red band. And first I'm adding them together on the top, and on the denominator side, I'm subtracting them. And then I'm getting that NDVI, which is in the range of 0 to like -1 to +1. Okay, and then I'm going to visualize that one. So I'm going to visualize, you see, I'm specifying the range from 0 to 1, and then I'm using the palette, like the visualization palette is NDVI, and then I'm adding the layer and everything. So this image, like this is, you see, this is for the whole world, and just doing that processing, just in a matter of seconds, you are able to calculate that one. So that's the, like the charm of the Google Earth engine. Like if you have to do this on your local machine, you can never imagine like how long it would take. It just like just loading the data, it might even crash your like the software. It takes a lot of time. But here, within just a like sometimes or even within a fraction of second or within just a matter of seconds, you are able to calculate. So once we have this NDVI one, like I said, for the classification one, you can do that for the like the uh, further processing. Like from 0 to 1, 0 to 0.2, you can specify that as a like the barren land. 0.4 to 0.5, the 0.6, you can specify another vegetation classes and so forth. Okay, so here, this is how you do it. So I'm just giving one example of the NDVI one. We have another example with NDWI, or even for the fire detection, like the fire, like the pre-fire data, post-fire data, how much area has been burned, all those kind of stuff. Like if I see, I have another example. Where is let's see, like land cover classification using this is using local machine. I have using, so you can use in like the NDCI one also. I have like all those application side. I have, like this one is for one of my classes. So but like I'm just giving you the basic idea. Like this is like one, just calculating that one vegetation indices. Okay, and another one is you are going to calculate that EBI, another vegetation indices, which is like for the EBI one, this is the formula, and then you are using near infrared band, red band, and blue band. Okay. Similarly with like another one for the NDVI one, you see that one is for the NDVI. And then after you calculate that and everything, you can export that either as a numpy array or the GOT, like the file format, like for let's say for the printing, for like the dissemination of your result. Like you can export that as like you can do all your calculation processing on that platform, and then after you are finished with that one, you can export your result as well. Okay, you can clip your area, like on this one I have, like for that Landsat, like the SRTM, which is the elevation one. I'm just like the selecting my area of interest, which is like a not the like a one step, because for downloading the whole United States or for the whole world, in terms of volume of the file or the size of the file, it's enormous. So for your area of interest, it might be a small area, then like you can do the processing and then export that. Like here I'm just selecting that one area of interest, which is like state of North Dakota, and then I'm going to export that one. And on that one, like once you have the data, you can visualize that using numpy array, and also you can export that as a geotiff one. Like here you see this data, you see on this, you see one of the caveat drawback is, you see on this image, the way it looks is because of that, like the cloud noise. Like we have to deal with those kind of images as well on the multi-spectral hyperspectral one. Okay, like although I'm going to like export the data, but this one is not a good data, so I can do like the filtering, all those kind of stuff to get that one. And then you can also like export your image collection, and then once you do that, it's like you can specify to download on your in the like the Google Drive, like whether Google Drive or even on this folder, and from that one you can download. So yeah, that's all for this one. Let's see. Mm. So if you have any questions, so this is the. mm, So yeah, if you have any questions, let me know.
Uh, Thank you, sir. That was such an insightful and engaging session. Thanks for guiding us step by step through Google Earth Engine and helping us gain practical experience in analyzing satellite data. So, like moving ahead, we will have a quick Q&A session. If
Mhm.
you have any question regarding Google Earth Engine dataset, band resolution, or analysis technique, please feel free to post them in the chat box.
So one question is, which are the different ways to validate results obtained by hyperspectral image processing or multispectral image processing? Like we have this, like we go to the one is like this one, the example that I showed is like the basic one. But if you are going on like the validation one, then you go to the field, collect the data, like the label the data, and then validate that one. Let's say like the land cover classification example. So you want to classify into different like the feature. So on that one, let's say on my area of interest, I want to classify 5 different classes, like forest, like water bodies, agriculture, barren land, and the built up area. So I will be like collecting the information in like the extracting the information on the field. Let's say for each of those classes I collect like 10 10 like the information like 10 20 like based on that one, and then you can do that in like the validation, like the pixel information that you have got from the classification and from your level feature. You do that like the accuracy assessment, all those kind of stuff you can do that later on, because on that one I'm just giving example, like how to acquire the like the like the for this particular like the presentation or the session, we are just concerned on how to acquire the data, where to acquire the data, what are the different information that we can get. Like the question that we have asked is like the further analysis, like it requires like the machine learning techniques, like the validating the data, all those like every other like like the multi, either it's for the multispectral one, hyperspectral one, SAR one, we have to do the validation, which is collecting the data on the field. So one way is, one example way is like using that Google Earth Pro, like on the Google Earth Pro, let's say on the Landsat one, which is like the 30-meter resolution, you don't see a lot of detail on that one. But if you use like Google Earth Pro, it has a lot of information on that one. So like on the pixel size, if it is actually like classifying that feature on the land, you can like for that location, particular location, you have this X and Y point like latitude and longitude, and then you insert that point to the Google Earth Pro and then see on that picture, okay, whether it is actually classifying that as a forest or not, whether it is actually classifying that as a agriculture or not. So one easiest or like the cost effective way is using that Google Earth Pro. But the best one is if you go to the field, but that all depends on how much funding do we have, time and resources and everything. But we have been using like Google Earth Pro most of the time. Okay. Okay, to process hyperspectral image using Python, which is the most efficient and accurate tool. So most of the time, like when we are doing processing for the satellite imagery, so like the packages, one is for the raster data is the GDAL. Then we have this rasterio, like the NumPy, scikit-learn, like for the machine learning one. But the most commonly used that we use for the mostly for the raster one is rasterio, uh, GDAL. Like those are the most commonly used one. And in terms of like the efficiency and accuracy, it's all. What are the some real world projects using? Okay, in terms of real, like I said, like the application one, land cover classification. You see it like that land cover classification, it has a huge implication. So like you classify area into different classes. So after you classify that feature, let's say I want to calculate the carbon, how much carbon has been like has been segregated, like the sequestered on that area. Or let's say a fire occurred on a certain place. Like every summer we have this event of fire occurrence, even in the US, even like everywhere in the world it happens, that one. So you want to like calculate like how much property has been destroyed, how much like the forest has been destroyed, how much like where the fire occur, like what has been destroyed and everything. You want to show before fire, after fire, like the like one is for the change detection, like what changes we have seen on that part. Okay, so real world is like one is the like land cover classification. Using that land cover, like we have this land cover, I think like on the US side we have this national land cover data set, which is like NLCD. So they have this data already like the updated on a yearly basis, and using that data as an input, every like other people have used that for let's say for the environmental application, like the species biodiversity, like the species modeling, like let's say let's say for the like the housing or the like the real estate one, if you want to build a house, so for that purpose you want to see, okay, I want to build a house that should be nearby to the school area, that should, like, I want a peace area, like it should be covered by the forest, it should be nearby to the water bodies, land, like all those kind of features. We extract that feature using this satellite imagery. So on the real, like the earth engine side, we have that done, like we have done that one. And this one I'm giving just example with the environmental application, but we have that massive use on the disaster management, mineral exploration, like all those kind, like even on the uh, or the, like the defense as well. Okay. Yeah, thank you.
That brings us to the end of the Q&A session. So we would like to present you with a small token of gratitude as a gesture of our appreciation. We are truly grateful for the practical knowledge and clarity you shared with us today. Our participants gained valuable hands-on experience in satellite data analysis. Before we conclude, we have shared a feedback form link in the YouTube live chat. We would like to request all the participants to kindly share their feedback with us. Your inputs are extremely valuable in helping us improve and design future sessions that are even more impactful and engaging.
So thank you once again for joining us, sir. From understanding sensor evolution yesterday to practically working with satellite dataset today, this journey from pixel to precision has truly come full circle. Lastly, we would like to thank you all for being such an attentive and enthusiastic audience. We hope today's hand-on workshop has given you the confidence to explore and analyze satellite data independently using Google Earth Engine. We look forward to seeing you again in future sessions and webinar. Thank you and have a great day.
Yeah,
Thank you.
thank you so much for your time. And if you have any questions, like, because this is like the basic understanding, like I have just covered with the multispectral one, but on the demo version we have for the hyperspectral one, SAR one, and on the application side and everything, it's another one. So
Yeah.
that is another session. So if you want to go on more detail, or if you want to know more, like the like sharing the resources and everything, you can contact me. I think I have your I've shared my email address and everything, so you can, if you have like the personal email, like the questions and everything, if you want to know more on detail, then you can reach out to me as well. Yeah, and thank you for your
Sure, sir.
time and everything. Yeah,
Yes.
bye.
Yes. Sure. Thank you, sir.
Thank you so much.
Yeah, bye.